Hello. Hello and welcome to the next talk in this beautiful, beautiful tent. It's about 3D printing, so we finally get to know a really practical application of 3D printing, which is just medical devices. So please welcome our next speaker.
Hello, thank you very much for coming tonight. I know it's a bit late. Thank you for being here. My name is Tarek Lubani. I'm a Palestinian who lives in Canada. I work as a physician, as a doctor, both in Palestine, the Gaza Strip, and in Canada. I want to start my talk for you today by talking about some medical devices and what it is that brought me into them. I start that by telling you a story. And actually, to really explain this idea to you, I have to tell you two stories. But I'll start with this one first. And it's a true story about the humble stethoscope. Now, you've probably seen a stethoscope. If you've ever been to a doctor, you've definitely had one put on you. One moment while we see what happened here. Let's try that again. This, of course, is the stethoscope that most people are familiar with, or some variation of it. Now, this particular stethoscope is apparently some very big technology. Well, it really must be, because the costs for it are quite exorbitant. It costs, for that particular stethoscope, about $200 US. Which seems kind of ridiculous when you think about it, because this particular stethoscope contains absolutely no new technology. I mean, no new technology. This here is the patent that covers all of the workings of the modern stethoscope. You'll notice from the date that it's dated 1963 for the patent issuance, 1960 for the patent filing. Even in the United States, that patent has expired. It's long expired. There was some additional work done on stethoscopes after this, mainly by one small group of people. They sort of modified a little bit how to listen. This particular patent covers the modern Littman Cardiology 3, the main stethoscope. I brought them all with me. That's this head here, which you'll see in a moment. And then after that, there was just a little bit of work making it so that you could listen one side or the other. And finally, when those patents were about to run out, this particular stethoscope here, which is the most expensive one you can get, you see it right there, and you see it right here. The most expensive stethoscope money can buy. Why? There's no good reason for it. There's no good reason for it. And that's what brings me really to my second story. I told you that I had two. My second story is a little bit more personal, a little bit more intimate. And it's also a true story. This one is about death. It's the kind of death that you would sort of expect. It's not about a story that's really about the different sorts of things that I've seen in my life. For example, I was at this particular massacre in Egypt, where I would do what people in the 1800s did, put my ear to the chests of patients. There is no new technology, there's no old technology that would change the fact that when you do not expect hundreds of people to be massacred, you will not be carrying a stethoscope with you. But that's death in the field. And that death in the field is really, for our purposes, not relevant. What I want to talk to you about is death in a hospital. Because that is one place where technology matters. That is one place where it matters what we do and how we do it. And so when I was in the war in Gaza Strip in 2012, I witnessed all kinds of things. And I had to hold my head to the chests of patients because there were no good stethoscopes. And that was a tragedy. that was a travesty, that was unacceptable, and that was something that I couldn't have. And it's not just me, it's a lot of people, but when you have this particular problem, you ask yourself, well, what can I do? The problem is so much bigger than I am. The problem is so much greater than I am. What can I do? And that's when one day I was playing with my nephew. And I saw that my nephew had this stethoscope, which cost $1. I picked it up, I listened to it, I put it on his chest, and guess what? It didn't suck. It wasn't terrible. Somebody with probably more talent than they should have had developing this particular toy banged it together in what had to have been a week or 2 or a month. Put it together so that it could be manufactured for pennies. And I thought to myself, well, why can't I make this? This is my stethoscope, my personal stethoscope. You even see my name engraved on it. This is the last stethoscope I will ever buy. Because when I started looking at this stethoscope, I realized that, hey, it doesn't have to be this way. This is when I learned to make a light blink. And that opened the whole world to me. And I realized, looking at this Arduino and that blinking light, that there was no good reason why we couldn't do this. Why that community of hackers who spent hundreds of hours doing beautiful things can't spend those hundreds of hours doing beautiful things in the medical field. It was that flashing light. That's what got me. And here came my 3D printer right after that, and I thought, why not? There was a problem, though, and that problem was that I don't know shit. I really don't. I know medicine, but I don't know anything else. So I got onto the RepRap IRC channel, and I started asking, does anybody know what we're doing? Does anybody know how I can progress? And there was one person, actually, who answered that call. Probably here, actually. I can't quite see the audience, but I bet you he's here. Yeah, there we go, the hand waving. Clement was truly an inspirational part of this story, an understated one. And when he looked at this problem, he understood the potential. And he said, we need some friends. And so the merry gang of sort of bandits, as it were, started coming together. This is Jennifer Glausch, also here. Saw her earlier. And off we went. Off we went. And we had to ask ourselves, what should we do? What should we make? We made a list of these priority projects, these things that if I could bring them into Gaza, if I could bring them into the third world in which I work and live, if I could have some of that with me, then I felt like I could change the lives of my patients. I could change the lives of the people around me. They deserve good health, and I wanted them to have it. This is Jen's first iteration of the stethoscope head. And with this first iteration, what we had was the beginning of a project. What we had was a model that we could then see how it would work. By the way, it was terrible. And within a few days, we had another version, slightly less terrible. And then one day, I took this very model here, actually, and I put it to, I think, my own chest. I forget whose heart I listened to. And I thought, we got it. This particular head cost 30 cents to produce. I don't know what that is in euros, like 2 euro cents or something like that. It is the hard work of quite a few people, dedicated people. It cost less than 10,000 euros to develop, and we put it out, obviously, for free, obviously. I wanted the people I worked with to be able to take it and to print it and to make it and to improve it, because I knew that all I wanted to do was just sort of bring the idea and then have other people take it and do better. Because, as I'm constantly reminded, I don't know shit when it comes to this stuff. So let the smarter people figure it out. Here's some other shots of this. And so what we had with us was a stethoscope exactly like my nephew's, a piece of plastic made by some merry folk who wanted to try to do something. And then the next question became, how can we prove that this is usable? Because here's a problem that happens in the third world. When you get out into the third world and you give something to the people who are there, very often it's crappy. It's being used on people to test things. It's substandard. It's not acceptable in the first world. And so I thought, I work in a first world institutional center. I'm an academic physician. I'm called associate professor, as it were. What is it that we can do here to test it? This is how you test a stethoscope. We made a very similar protocol. I didn't put in the photo because I didn't ask Clement for permission of it. However, it's what we call the Hello... I didn't put it in the presentation. Called the Hello Kitty protocol, because the only balloons we found when we were doing this project were Hello Kitty balloons. And it turns out that if you take a balloon and you fill it with water, exactly like this very sophisticated protocol, put a speaker to one side and a microphone to another side, you can test it. You can figure out how good your stethoscope is. And so instead of trying to run the physics, we printed stethoscopes. And we printed some with larger channels and some with smaller channels and some with larger infill and some with narrower infill and some with higher sort of intake and wider and narrower. And then we picked the best. We compared them all to the Littman Cardiology 3, the gold standard, the stethoscope I want on my patients. Here's our final product. This is an audio frequency response curve. Everywhere the blue is higher than the pink, that is the free open hardware stethoscope beating the Littman Cardiology 3 in performance. We did it. We got it. That head is as good or better. You see the large peak in the early sort of part of the frequency response curve? That gives doctors, when they're listening, the feeling of superior sound quality to the Littman Cardiology 3. I've put this stethoscope around the necks of many of my physician colleagues, and they've been using it for the past approximately 6 months. So have I. So have I. I've been using it in Gaza, and I've been using it in Canada. This stethoscope is as good as any stethoscope out there in the world. And we have the data to prove it. And so that ends the tale of the stethoscope. We have several other projects that are on the go. We have a pulse oximeter that is also going quite well and is ready basically for calibration in this special way. You have to take human beings and desaturate them. We have an electrocardiogram that is not quite as advanced. And after we're done those, we plan on doing dialysis. Those of you in biomedical engineering, those of you in medicine, understand that about those 3 devices, those are 3 of the most ubiquitous life-saving devices in any medical center. Those are 3 of the most expensive, and those are 3 of the easiest to beat. I haven't yet looked closely at the patents for hemodialysis. I can't imagine there's a patent there that's still valid. And so what we want to do is we want to take these devices one by one and do for them what initially started to be done for software when the free software movement began. replacing expensive, closed proprietary solutions. That was the dream of people who were making proprietary software maybe 25 years ago. Now, free software 25 years ago. Now, of course, free software beats and exceeds proprietary software in a lot of ways. If we do this, if we create this culture, if we go to places like Gaza, like parts of southern Africa, such as Botswana, Rwanda, etc., and create this culture, then in another 25 years, you'll see that there is an equivalent of Apache in the free hardware domain of medicine, that there's an equivalent of Mozilla in the free hardware domain of medicine. And that's not something that we want to own, that's something that we want to contribute to, because at the end of the day, that's what open hardware is about, and that's what the open ethos is about. So really, all of this is a pitch, because what I want is I want you. The people in this room have got to be some of the smartest in the world. You know the technology, and more importantly, because I've met some brilliant engineers, you understand the politics. What I want is not the best devices. What I want is the best devices that are also free. And with your help, we can make that happen. Now, what I'd like to do is to make this a conversation, to start picking at your brains and have you pick at mine. The Glia team, we call it Glia, it's on GitHub, it's GliaX, and I'll post that as well. If you look at the schedule, it's on there. The Glia team is all here. I'll answer any questions that I can. I want you to ask, and I want to figure out what you think we should be doing better and what you think we can do moving forward. So we have a good 15, 20 minutes, and that would more than easily put us way ahead of schedule. Thank you very much, and do you think we can take questions now, Marcel?
Hello? Okay, now it works. Thank you for the beautiful talk. Now there are two mics, as you know. There's one to the right and one to the left, so please just line up if you have any questions. We will start on the left now.
Yes, now the mic is on. So first of all
could you please introduce yourself as well?
Yes, I would very much like to introduce myself. My name is Lam, like L-A-M, like the Turkish word for boy, or like local area network, or like all left activist, neuron, or whatever. So look, you're talking about free medical devices. So you did just show two things to the audience. One of them is, one man is pretty tiny, as you are up there, because you're like alone there, you're one person talking to like a big audience, many people listening to you, just introducing your ideas to the brain neurons and kind of like saving it and maybe spreading it around. You do this all by yourself because you're tiny. At the same time, you're great because you're spreading an idea. And this idea is just awesome. And everybody in this room just got this because you really did your thing. You did awesome. You found something that is great for humanity, that is great for all of us. It's great for me, for my grandmother, for your granddaughter. It's gonna be great for everybody because this is free. It's free like water is free. You need water to live. Is there a question? You do need water to live. And you do need those things to be healthy.
Would you please mind just asking a question? Thank you.
Yes, like what can I do to support you?
Thank you very much, Lem. I appreciate the comment and appreciate the question. The main things, there are a few things here to support, and it depends on your competency. So for example, it's just like any open source or free project, Libre project. If your abilities in hardware, we need that. Grab the source, play. This is a small team of people who are trying to do a lot. We need help. If you have competence in management, if you have competence in design, Anything that you have competence in, great. Right now, the points of extreme dearth that we need are people who understand the science and know how to run randomized control trials and non-inferiority trials. And also, the other thing is people who know the engineering and are willing to participate and collaborate with Clement and Jen and others. Thank you, Lam.
Could we please get the mic on stage left?
Yeah, like my comment on that is like I actually also built a stethoscope myself, and I guess all the people, like many people here, can build a stethoscope because just building one is really easy. I figured that also out. I guess what we then as non-medical people would need is actually kind of your help in how to figure out if they actually work, because I have no idea if the stethoscope I built was any good. I could hear my heart beating, but like how, like I would be very interested in to actually learn like what all the little beats mean. But yeah, kind of, you know what I'm getting at, like we also need kind of like how-tos, how to actually build this stuff and then how to test them and stuff like that.
So what is the product of GLIA as an academic? It's basically an academic project right now within my academic work. What's the goal of GLIA? There's two products. One of them is the product, how to make it, the bill of materials, the STL files, the BRDs, the schematics, all that stuff. The second one is how to test it. Because if you're making something yourself, how do you know what it tastes like? You can bake the cake, but how do you know it's the cake that I want? And in that sense, in this particular case, you probably will not buy this particular, here are the stethoscopes I was talking about. Here's, and you're welcome to come here and play with them if you want. You can steal them, I don't really care. But basically with these stethoscopes, we've run the tests. There's the frequency response curve. That data is available. Grab the data and play with it. If you can exceed it using the test setup, which we'll affectionately call Hello Kitty from now on, then you've beaten our product. In which case, send a pull request. I'd gladly take it. Well, of course, once we verify it. So that's the way to do it. I don't expect you to be a doctor. In fact, it was one of the things that drove people crazy when they were working with me, because they would send me products. I would take them into work. I would use them. And I'd say, no, it's wrong. How do you know? I don't know. It's wrong. Until finally we started to develop some more systematic ways of figuring it out. The first thing we do in any project is set the specifications. And any good engineer will tell you that if you don't have specifications, you're going to run around in circles. So it's an excellent question. The specifications and the testing material is up there within the GitHub. Every project has a testing folder in it that says how we tested and how you would test to know that you've reached equivalency.
Thank you.
And you didn't introduce yourself.
I'm Malte.
Thank you.
Now stage right, please.
Hi, very cool talk. There are a couple of things that I thought about, Barbara Middleman, a couple of things I thought about when you were talking. One is that it's relatively easy on some level to engineer things that are relatively low tech. So a stethoscope, the information transfer is essentially from the chest to your ear. Doesn't require the same kind of information transfer that you have in, for example, a dialysis machine, particularly if you're going to be doing recording and need to be interoperable with the rest of the medical record and all of that sort of thing. So that's one piece of interest that I have in how you're thinking about sort of making this an end-to-end solution in a much more complex medical setting. The second thing, which you also spoke to at least peripherally, is about the documentation of how well engineered these are, what the performance characteristics are, and how they compare to what else is out there. And that's really about getting publications in the peer-reviewed literature, which is not really going to be terribly receptive to this because the reviewers aren't going to know how to review this in the places that you're going to need to put it. So I'm wondering, how do you think you're going to get the culture change that goes along with it? And then the third piece of it is about the kinds of low-tech engineering that you can do with 3D printing, for example, for prosthetics, particularly for kids, because kids grow, for assistive devices, for things where you really have a static piece of equipment, but that you may need to trade it out frequently. And so that this is something you also can take into the third world pretty easily if you can do it. So a bunch of different questions, a bunch of different axes in a sense of where you can go with it, but it's very interesting work.
So these are definitely things that I've been thinking about a lot, that we've been thinking about a lot, that I'd really love for you to think with us about. First, I think your first question was just in terms of the complexity of devices. We have picked the devices that are the most expensive, that is, that there's lots of parts to them, that people think should be expensive, but are actually the easiest to do. So for example, I've looked into the insides of lots of these dialysis machines that are broken and so on. It's just a peristaltic pump.
Right.
That's it. That's it. A peristaltic pump and an Arduino will probably do it. People have done it for $500.
Can you do a vent?
Sorry?
Can you do a vent?
Can
Ventilator?
you?
Can you engineer a ventilator like this?
So ventilator is very complex for a few other reasons. So we're going to go with things like dialysis first. Ventilators probably in the second tier, and then things like MRI, CT are in the third tier. But for this tier, I mean, all we need to do is to get a pump to push things from one place to another. According to Health Canada, and I'm pretty sure FDA would be the same, the device we make will not be a class 4, that is the most difficult class, because it doesn't itself contact blood. Instead, what it does is you can actually make it. One of the big problems in lots of these third world countries is that they kind of have to take what they can in terms of the disposables, and the disposables are what's really expensive. So if you could make a dialysis machine that could take any disposable, because why would we care? We're happy to make it interoperable. Why do we care? Then they can take any disposables, and the disposables are actually where the danger lives for the patient. So the disposables are the things you have to get right and the things we don't have to get right. Not now, later. Later, I have some ideas about that as well. Now, in terms of the peer-reviewed publications, yes, we have to peer review. Yes, we have to publish. That's how we're going to prove it. Otherwise, it's just a chart on GitHub repository. How will we do that? Well, we're going to publish. Where? Well, I mean, I don't imagine PLOS ONE is going to say no if the data's solid. I don't care where. I care that it's accurate and that it's respectable. And so long as it's those two things, then we can present it to people. The fact is that stethoscopes that are sold now don't have to be peer-reviewed and don't have to be validated. It's a class 1 medical device, which means that all you need to prove is that rodents aren't taking craps all over your product to send it off. And that's it. That's it. You have to be able to recall it so that if the rodents do, you can say, oh, I'm sorry, rodents and such, and then bring it back. That's a class 1 medical device. They need no evidence at all. We're already beating almost every stethoscope on the market right now. And the peer review, I think, is going to be a cakewalk, frankly. I think it's going to be easy. We've got solid data. We're using tested techniques. We took them out of peer-reviewed publications. We're using methods that other people use. This is not going to be hard.
Thanks.
Stage left, please.
I'm Fox, Phawx. I'm a neuroscience student and a hacker. You said you needed scientifically inclined people to run experiments, and so I have a three-pronged question for you. Have you decided on standards for running these experiments, for reproducibility and empiricism? 2, do you have a preferred data format to standardize the process? And 3, have you already chosen or selected a forum or database for data sharing?
Okay, let me go backwards from those. In terms of forum for data sharing, currently we have an ad hoc forum, which is basically just the GitHub repository. That's currently where our data lives. We haven't, as such, sat down and truly structured the scientific approach. And that has to do with a lot of parts. I'll come back to sort of my main thing. I don't know shit. So we're trying very hard to get people who really are in the know. You know, science research is like cryptography. It's a bad idea to roll your own. So in this case, we're trying not to roll our own. We're trying to bring in other systems that other people know. I have an idea what I think is a good idea, but what I've been doing is approaching people who know it takes a lot of time to do that. We're not yet done that. In terms of how to engage with that process or what format, it's going to be project dependent. For example, for the pulse oximeter, you literally, I I kid you not. You have to sit people in a room and desaturate them, give them non-oxygen solution until they become like at the edge of death, and then measure their blood work while you're measuring them simultaneously on another finger. It's insane. But that's the protocol. So that runs very differently. There's no such thing as a randomized control trial there. How do you, what do you do there to randomize it? Other things, yes, you can randomize. Other things, you kind of have to do just a standard non-inferiority like the stethoscope. We thought about, for example, doing a randomized control trial with a stethoscope, putting a sham stethoscope on people's ears and having them compare it, and then putting the Littman Cardiology 3 in there. These things don't always make sense all the time. The bottom line is, if you're interested, then please leave your contact information afterwards, or contact me. My name is Tarek, T-A-R-E-K. My email address is tarek@tarek.org. So easy. Email me or email anybody from the team, Clement Yanev or Jen Glausch, and they'll be able to sort of get in touch with you, put you in touch. Also, we're on Freenode, and it's in the channel OpenMed. Or if you hit RepRap, you can usually find me. My nickname is Orangey on that.
Will do, thank you.
Thank you so much, Fox. I appreciate it.
Stage right, please.
Hello, my name is
Hi.
Karen, and when I was listening, I was wondering, your device is out of plastic, right? So I would expect that to be pretty sensitive to cold and heat, for example. So I was wondering how sustainable it is in the sense of how long can you use your device or your head in comparison to other ones?
So there's a few parts to that. One of them is that the devices are incredibly cheap. So they're very, very cheap to manufacture. So if you can get longevity that's, a third or a half, I think we'll be fine. For the stethoscope, we just don't have enough experience with it for me to tell you that, it's as good as metal for as long as metal. There's no doubt it won't be. There's no doubt that a piece of metal will last longer than a piece of plastic. However, any place where we're going, for example, the Gaza Strip is a closed system. I don't know if you're familiar with the politics. There's essentially a hermetic seal around the place, nothing in, nothing out with, I'm oversimplifying, but basically. And so one of the important things was we didn't start until there was already a plastic processing system. When you finish with the setup, we set up a 3D printer, actually, which, coming back to the other question, is making prosthetics right now, because we found that much higher priority than stethoscopes. But when you set up a 3D printer, then we make sure that cheek by jowl, we also have a setup for something else that can generate filament, and that's context dependent. So in a place like the Gaza Strip, there's a very rich economy of people gathering plastic, taking it, grinding it into chips, and then making filaments out of it. They were already doing that before we arrived. Places like India, there's collectives of people, garbage pickers, who do the same thing. So you can find, those are sold. Those particular plastics, the Indian plastics, aren't preferred. They're HDP, which if you're a 3D printer, you don't necessarily want to print with. But there are lots of good, usable plastics. Coming back to the initial question of longevity, I don't know, but I think it'll be good enough for our purposes.
Stage left, please.
Hello, Jans for introduction. So I'm known on campground as Mad Dog. I've been working as a physician in some troubled areas of the world, sometimes with not little more than my bare hands. So I'm very fascinated by your idea. So please allow two questions. First is, did you think of preparing surgical devices as well? And second is, do you think of, in future, maybe foundation, task force, anything to bring your equipment or production equipment to such troubled areas?
I'd love to talk to you offline about this. It would be really amazing to do that. Surgical tools are a big priority. We already have a repository of surgical tools that we've been testing. And right now we have a inadequate needle holder that's in progress. It's actually significantly improved. And in fact, I am the weakest link in that production because I'm the one who's testing it. So if you'd like to test these devices, and I'd be happy to set you up with a 3D printer if you don't already have it. it would be great to have somebody who can actually be testing them. So the surgical devices were easy to basically, I mean, maybe Jen should answer this. Easy for me to get Jen to do, where basically what it came down to was that we sent her a bunch of these devices, and then she started manufacturing, or rather creating them using a little bit of a derivative that created open SCAD files. Surgical tools, I'm with you, they're essential. But surgical tools, while they're a class 1 device, we can't mess around with that. So I wanted to get some experience. I think of the stethoscope like our calling card. It's a way that you can, in a very concrete way, show to somebody what you're doing. It's very simple, very few moving parts, almost no risk of failure. So if it fails, stick your ear to the patient if you really need to. So that's why we started there, and that's why that's the first project that we're using to talk to people. You can understand it very easily. Whereas if I were standing here with, forceps, it would be much harder to sort of explain what we're doing.
Second question about structures for deployment. Do you have thoughts, plans?
Oh yes. Well, I can talk to you a little bit about the failures that we've experienced as a group. Initially we tried to create it as a bit of a non-profit, and that didn't quite work because immediately when you instate something in any kind of corporate framework, people will look at it very differently. So right now we're in the midst of a transition to have it be an academic project, like a genuine, true academic project. We had initially avoided that because we wanted to open the ability to get funding in a few different ways. But having said that, what we ended up doing is, I think now, migrating back to the academic ideal, since really, frankly, the project will never make money, and in my opinion, never should make money. It should only make devices.
Thank you very much.
And I think I see Jen at the microphone. Did you want to say something?
Yes, hi. My name is, by the way, Jennifer Glauche. You pronounce it wrong.
Sorry.
You had a question right now, but I forgot what this was about. So
we were just talking about the manufacture of the surgical tools. Yeah, that's it. And how I'd sort of tasked you with them, and they were difficult to do. And
they're not really thrilled to do. I made a talk, by the way, for Chaos Cologne earlier this year. And, well, you can look up my talk on the CCC video page.
Thank you so much, Jennifer. I appreciate it.
Thanks.
Could we get stage right now, please?
Hello, my name is Marius. I'm the author of a software called OpenSCAD, which I believe is the tool you use to design your 3D prints. And I just want to say, how can I help? How can I make your life easier?
Well, firstly, I just want to say thank you. I love OpenSCAD. It's been really wonderful. So thank you. Also, I feel really honored to meet you. So it's a privilege of mine. Right now, I think in terms of how to help, we've definitely hit into lots of limits in OpenSCAD. And I would like you to maybe commune with Jennifer. She's probably the best person to talk about some of the limits that we've hit. In terms of how to go forward, I mean, you clearly have the software knowledge and software tools. So it would be really great to talk to you afterwards and see what you're thinking and where maybe there's room for collaboration on that. I would find it very hard to believe that there isn't massive room for collaboration. Yeah.
Thanks. I'm sure there is.
Thank you.
Stage left.
Hi, I'll identify as Tatzelbrum, and okay, I have some academic degrees, piled high and deep, and I'm a little involved in medical devices. And I am kind of wondering, I mean, first of all, it's great what you're trying to do. You're trying to make medical devices actually really open source and free. And I am wondering whether you shouldn't go ahead and actually publish everything under something like Git. Because, I mean, something that makes medical devices expensive are artificial scarcities. and gatekeepers, and both the regulatory institutions and the academic publishing industry are gatekeepers that create unnecessary scarcity. So I'm wondering whether it would be feasible to make the jump and go completely open source in Git repositories in the cloud, even for the scientific publication part.
I love your idea. Done. There's the GitHub repository that I brought up. I don't know if you can see it in your screen there. Basically, it's github.com/GliaX, just because we couldn't get the Glia one. Here are the repositories: Stethoscope, PulseOx, Meta, which is kind of where we're trying to assemble back to Fox. I don't know where she is right now, but okay. Where we were sort of assembling how to do the overarching project. The ECG repository, Gauze-Loom. Actually, do you mind if I tell you a little story about gauze? During the war last year, exactly a year ago now, Gaza ran out of gauze. Like, there was no gauze, which is deeply ironic because the word gauze is actually derived from the word Gaza, because the first gauze ever made historically was made with Gaza processed silk called gazatum. Anyway, that's just a silly factoid there.
Okay, but the actual question there is, okay, I've already seen this GitHub, and I'm going to link it. But the question is whether you could even put the first publication of your actual science, on the GitHub first.
Done. It's all done. I tell you, we're not doing anything that's not public here. So the stethoscope, okay, I need to fix the testing readme.md, and I just haven't gotten around to it. But here's all the data. Here's the WAV files that we use to make this. Here's the setup. Here's the PNG files, the plot data. We used open source software. Well,
I mean everything but the journal paper. I mean, I'm serious about the journal paper should also be there, and
there's
be there
no
first.
journal. I haven't written it yet, but what I have done is where's the README in this thing here? There we go, stethoscope validation. This is more or less the paper as it'll be published. I apologize, the photos there, because I moved the directories. The photos don't show up any longer, but it's there. Once the publication is written, it'll be there. I'm not interested in pursuing things in the traditional manner of waiting an embargo and so on.
So this was the droid I was looking for. Thank you very much.
No problem. Maybe a bit of background there is that before this, I was involved in a now defunct, unfortunately, medical journal called Open Medicine, which really had the goal of publishing everything in the open, had the first Wikipedia sort of journal articles and so on. So the philosophy is there. The philosophy is definitely there. I'm a free software, free hardware fanatic is maybe a way to describe it, or fundamentalist. I don't know, maybe that's the only place where as a Palestinian, I'm allowed to call myself a fundamentalist.
Stage right, please.
Hi, my name is Bruno. I have a question for you. Aren't you afraid that medical equipment companies are going to try to sue you out of market?
They can have everything I've got. I don't care. The real question is, what are they going to sue me for? So everything that we're doing is actually covered under patent. We're just making things that they've already patented.
Yeah, that's the point. If they own a patent, they can sue you because the
legal advice that we got was to work out of their expired patents. So we have. So the reason for that is because danger lives in innovation. So that's not where we're going first. There's a lot of medical devices that have been out of patent for many, many years. The first stethoscope was in Victorian times, basically men who didn't want to put their ears to the breasts of women. And really, the stethoscope was done by 1965. By 1984, everything you know about the modern stethoscope, that is this one, which is Littman's most lucrative one. This is called, I think, the cardiology specialist or something. Anyway, everything is done. as of 1984. And after that, all of the patents have to do with electronic stethoscopes, which I think Dr. Mad Doc can tell you, electronic stethoscopes are terrible. Unless you're hearing impaired, they're no good. So I'm not worried about being sued. I mean, it's part of an academic project. Good luck to them. But I think the other part as well is that we live in this very beautiful space. The people who are taking our products could never afford theirs. A Littman Cardiology 3 costs 1 month's salary for a doctor in most of the places where we are. There are no Littman Cardiology 3s in Gaza. In fact, in a hospital that has coverage area of almost 1 million people, there's things like only one otoscope thing to look in your ear. There's 2 or 3 stethoscopes, and they're all cheap ones. So these aren't markets where they're going to feel the hit, and they're not going to notice it. You know, I'm not that worried. And
So,
if they assassinate us, well, I mean, you guys can carry on GitHub, no problem.
Good luck with the lawyers.
Thank you, Bruno.
Stage left, please.
Hi, I'm Evan. I just was wondering if you could comment on sterilization with plastic versus metal.
And in terms of sterilization, thank you. In terms of sterilization, the method that we're planning on using right now is basically non-heat-based sterilization. So chemical sterilization and gamma ray sterilization. So these are very adequate, very working methods that are time tested. So no problem. However, I actually have a hunch that sterilization is not as important as we think. And one of my academic goals in the next 10 to 15 years will be to prove it, so that people can make sterile equipment, for example, dialysis catheter, which is very, very important and currently is made sterile. People can make those in a kitchen sink and then sterilize them post facto using, for example, alcohol, which is widely available, or UV radiation, which is widely available, things like that. So I have a hunch that it's going to turn out that you don't need them as sterile as we think, so long as you're willing to accept a couple of things. But that's the goal. Otherwise, if we need to make metal, I mean, you can just do like, I think it was Jury who'd been doing sort of stuff with metals where you 3D print things and then you would do I forget what the process is called, lost casting or something. I forget. Thank you.
Okay. Do we have any more questions anywhere? So I can't see anybody. Okay, then please thank Tarek again.
And I want to thank you all for being here and thank you all for listening. If you'd like, I'll be here. We've got another 12 minutes of this session, which I'd love to have just kind of as a free talk with whoever's interested. So come on up. And if you'd like to give me your contact information or take mine, my email address is tarek@tarek.org, or you can find us on GitHub or on Freenode. Thank you.